Hello, and welcome to second session of Computational Fluid Dynamics course by Mister CFD team. In this session, we are looking to enter Finite Volume Method field. Let's start with some simple examples and increase our knowledge of Finite Volume Method approach of CFD to a level that from the next session, enter the Fluent equations and methods. The first problem that we are going to solve numerically is heat transfer in a solid rod. So consider a one-dimensional rod that temperature at the one side of it is 20 degrees of Celsius constant, and temperature at the other end of rod is 100 degrees of Celsius. The length of rod is 5 centimeters, and the rod is very thin. The general form of transport equation is presented here. For energy equation, if we replace phi with internal energy, that is specific heat multiplied with temperature, the following equation will result. Three source term is added, first one because of pressure gradient, second one is because of dissipation, and the last one is volume source term. The rod is solid and also the problem is steady state. So, transient term, convection term, dissipation and pressure terms are zero, an equation for pure diffusion will result. Now, let integrate equation over a control volume. By using Gauss's divergence theorem, we can convert the volume integrate into a surface integrate of control volume boundaries. Now we should generate grids on the rod. The first step in the finite volume method is to divide the domain into discrete control volumes. Let us place a number of nodal points in the space between A and B. The boundaries, or faces, of control volumes are positioned midway between adjacent nodes. Thus, each node is surrounded by a control volume or cell. It is common practice to set up control volumes near the edge of the domain in such a way that the physical boundaries coincide with the control volume boundaries. For example, this rod is divided into 6 control volume. A general nodal point is identified by P and its neighbors in a one-dimensional geometry. The nodes to the west and east are identified by uppercase W and E respectively. The west side face of the control volume is referred to by lowercase w and the east side control volume face by lowercase e. The distances between the nodes W and P and between nodes P and E are identified by delta XWP and delta XPE respectively. Similarly, distances between face W and point P, distance between node and west surface boundary of control volume, is denoted by delta XWP, and distance between P and face E, distance between node and east surface boundary of control volume, is delta XPE respectively. The control volume width is delta X. Now we can discretize the equation on control volumes, cells. Here, A is the cross-sectional area of the control volume face. It's a very attractive feature of the finite volume method that the discretized equation has a clear physical interpretation. This equation states that the diffusive flux of T leaving the east face minus the diffusive flux of T entering the west face is equal to 0. It constitutes a balance equation for T over the control volume. In order to derive useful forms of the discretized equations, the interface thermal diffusion coefficient K and the gradient of temperature respect to X at east face E and west face W are required. Let's consider a uniform grid. Now with Taylor series that we learned in the previous session, we can write value of thermal conductivity at the node W and P with the base point of lowercase w. So, if we write Taylor series till second term and truncate higher order terms, these relations will result. So by adding thermal diffusion at nodes P and W and divide by 2 thermal diffusion at face W will calculate. In the same way, we can show that thermal diffusion at face E is average of thermal diffusion at nodes P and E. Because we use information from both sides, this technique known as cell central differencing. Also, if we write temperature at point W and P in base of W with Taylor series till third term and truncate higher order terms, we will have these equations. So by differencing these two, first and third term will vanish, and only the derivative of T respect to X at W remains. In the same way, derivative of T respect to X at face E can be found. Now, by replacing thermal diffusion and temperature derivative at faces with relations that we found, the following equation appears. Now, by more assumption of constant thermal diffusion, we can simplify this relation a little. So by considering the constant thermal diffusion value of K at the point E, and the P is equal. So Ke plus Kp divided by 2 is equal to K, and we can cancel the value of K at 2 terms. Also, the cross-section area can be canceled, and the delta X is also constant and can be canceled at 2 terms. So let's see what we found. The temperature at the point E minus 2 times temperature at the point P and plus temperature at point W is equal to 0. So that means the temperature at the point P is the average of temperature at nodes of east and west. But for the first and last nodes that bounded with boundary condition, we cannot discretize with the central scheme. The west face of first node is discretized with forward, and east face of last node is discretized with backward scheme. And you can see the relations here. If we define the points from number 1 to number 6, we can write the differential equation for each point. So for the point 1, we can write at the temperature T1 is equal to 2 multiply 20. That is the boundary condition plus T2 divided by 3. And for the temperature at point 2, T2 is equal to T1 plus T3 divided by 2. And with this manner, we can derive 6 equations, and we have 6 unknowns. We can write the equations in a matrix form. For example, if we write the matrix of equations system of this problem, the following matrix will appear. We can solve this equation with the MATLAB software. Results are shown in graph. If we solve equation of diffusion analytically, the result will be linear change of temperature from the two-side of rod. So in this figure, we can see the exact solution of equation and the numerical result. In the next work of this chapter, we discuss the cooling of a fin by means of convective heat transfer along its length. Convection gives rise to a temperature-dependent heat loss, or sink term, in the governing equation. What is shown in figure is a cylindrical fin with uniform cross-sectional area A. The base is at a constant temperature of 100 degrees Celsius, and the end of fin is insulated. The fin is exposed to an ambient temperature of 20 degrees Celsius. One-dimensional heat transfer in this situation is governed by this formulation, where H is the convective heat transfer coefficient, P the perimeter of fin, K is the thermal conductivity of the material, and T infinity is the ambient temperature. Problem is this: calculate the temperature distribution along the fin and compare the results with the analytical solution given by TB is the base of fin temperature. Like the previous problem, by replacing phi with internal energy and adding source term and some simplification, the differential equation will result. By integrating this equation over the control volume and some simplification, we can reach this new equation. The first and second terms are the same as the previous problem, and the third term is a constant at each control volume, and just multiplied to the volume of each control volume, A delta X. And then for the first two terms, again, we can discretize with the central scheme, like the previous section, and the third term doesn't need the discretization. So the algebraic equation is obtained. By multiplying equation into delta X and rearrange, this form will result. In the following, the final algebraic equations are listed. The first equation is for internal nodes. The second equation is used for first node near the base. So there is not any west nodes, and we must discretize with the forward scheme. Temperature of west face is 100 degrees Celsius, and distance between grid point and west face is half delta X. So if we rearrange the formulation in the formulation, the coefficient of Tp is not 2 and will become 3, and Tw is replaced with 2 times 20. The third equation is derived for last node in the end of fin. We know that end of fin is isolate, so this term will vanish from equation and only Tp minus Tw remains in the right-hand side. The total length of this film is 1 meter, and we have 5 nodes, so the delta x would be 0.2 meter. By replacing the values in the equations, the 3 equations will be generated in this form. Also, by rearrangement of these equations, the final system of equations will obtain. So for the internal nodes, the temperature at the node east minus 3 times of temperature at the point that we want, plus the temperature at west is equals to minus 20. For the first node, the temperature at the east minus 4 times of the temperature of the first node plus 200 equals to minus 20. And for the last node, 2 times minus temperature at the last node plus temperature of the west node must be equal to minus 20. And by arranging the equations in a matrix form, the final form of algebraic equations will generate, and we can solve this system of equations with a software like MATLAB. In the graph that presented, we can see the numerical results and also the analytical exact solution for the differential equation, and we can see how close these solutions are together. By using smaller grid size, we can even improve our numerical results. For the third and final example in this session, we are going to solve the x velocity in a channel with the length of 1 meter and width of 0.1 meter. Water enters to the channel with uniform velocity of 5 meter per second, and derivative of u respect to x at the outlet is 0, and the velocity at the walls is 0. Also, we need a further assumption of 0 y velocity to decouple x and y momentum equations. This is a very good assumption for this problem. Let's start with the general transport equation for the property phi. If we replace the property phi with the x velocity, x momentum equation will result. In this relation, the first term, transient term, is 0 because our problem is steady state and also the source terms are 0 too. The final equation will be in the form of following equation that includes convection and diffusion terms. Now let's integrate equation over a control volume. By using Gauss's divergence theorem, we can convert the volume integrate into a surface integrate of control volume boundaries. Now we should generate the mesh. For the grid generation, we divide the length of channel to 50 grids, and also we divide the width of channel to 5 grids. So the total cell counts for this problem is 250, and delta x and y are 2 millimeters. Value of x velocity will calculate at each cell numerically. For simplicity, grids are uniform with equal length and width. For discretizing the two-dimensional mesh, let's consider a control volume with its neighbor cells. Node that we talk about is named with the P. East node is named with uppercase E. The west node is defined with the uppercase W. The top node is defined with the uppercase N, and the bottom node is defined with the uppercase S. An east face of the cell is defined with lowercase e. The west face of the cell is defined with the lowercase w. Top and bottom face of this cell defined with the lowercase n and s respectively. Also, the positive direction of the x and y direction will be in this direction of I and j. I should also note that u appears as a scalar in this formula, so it can be come out from the integral. Velocity of v can be resolved into its principal components in the I and j directions. Velocity in the y direction is assumed to be 0. In the west plane, the direction of the plane normal and the velocity in the x direction are opposite, and so a negative appears in the formula. But in the east plane, the direction of the velocity and the plane normal are the same. In the south plane, the direction of the plane normal and the velocity of u are perpendicular to each other, and u dot dA is 0. The same for the upper plane. So, the integral will convert to a two-term of minus draw times u in the power of 2 times the dA in the west phase, and draw u in the power of 2 dA in the west face. dA can replace with the delta y, and the draw is constant. So if we write the u in the west note with the Taylor series with the base of face w, we can write that uw minus u prime multiplied to the delta x divided by 2, and half delta x is the distance with the face and node of west cell. With the same way, we can write the Taylor series for the x velocity at the node P, and by add this 2 together, u prime terms cancels, and we can write uw plus u at the point P is equal to double u at the face W. So x velocity at face W is the average of x velocity at the nodes the west and P, and also the x velocity at the face E is the average of x velocity at nodes E and P. So for the discretizing the second term in the right-hand side, mu is constant and comes out from the integral. And also, the gradient of u can split into terms of first derivative of u respect to x in the I direction and first derivative of u with respect to y in the j direction. So for example, if we look at the left face or the west face, the derivative of u respect to x and dA are in opposite directions, so a minus will appear in the formula. For the right or the east face, we can write the du over dx times delta y. And this first term is in the west face and the second term is in the east face. And also, if we look at the first derivative of u with respect to y and the normal vector of the west face, these two are perpendicular to each other, and dot product of these two will be 0. For the north, the dA and du over dy are in the same way, and they can add to the formula. We can write the Taylor series for the x velocity at node W with this formula. The uw minus u prime of W times delta x divided by 2 plus u double prime at W, that is the second derivative of u respect to x multiplied to delta x in the power of 2 divided by 8. By differencing these two terms, first and second term will cancel, and only first derivative of u respect to x at face W remains, that we can calculate in terms of x velocity at nodes W and P. In the same way, we can calculate the derivatives of u respect to x and y's in each face, and the result will be in the form of relations that have been presented here. Now, by replacing the relations that we found for the u and the first derivative of u respect to x and y, in terms of x velocities at a nodes, we can find this formation. By considering the equal values of delta x and delta y, we can obtain this formel. Also, by a further simplification, the x velocity at the node P can find its form in this formula. Now, what about the first cells near the inlet boundary condition? In these cells, the velocity at the west face is constant 5 meters per second. And now, for example, if we discretize as the left-hand side term, minus rho uu delta y in the west face plus rho u in the power of 2 delta y in the south side. In the west face, the velocity is 5 meters per second. U in the power 2 will become 25. Minus 25 rear delta y plus rear up plus ue divided by 2 in the power of 2 delta y. And for the second term also we can split the gradient of u to the first derivative of u respect to x and y. And if we calculate the derivation of u respect to x in the face of west, We can write the UP minus 5 divided by half delta x, because the distance between the face and the note is half delta x, and the rest will be the same as before. And the by simplification, we can write the mu times negative 5u in the p plus 10 plus u in the east, u in the south, and u in the north. Now let's talk about the cells near the outlet boundary conditions that the first derivative of u respect to x at this boundary is 0. So for the discretizing the left-hand side, because the gradient of u respect to x is 0, u at the east face of these cells are equal to up. And we can write this term this form. And for the second term also, we can discretize the gradient of u in the same manner of the previous steps. But the gradient of u respect to x in the east face is 0. So after simplification, this form of algebraic equation for right-hand side will obtain. Here you can see the discretized form of equation for internal grids, and also the discretized form of equation for the boundary cells of inlet, outlet, and the upper and bottom sides. Also, you can see the discretization form of formulation for the grids in the corners. This type of formulation is called implicit, because the UP that we want to find its value also appears in the right-hand side. And for the solving the implicit system of equations, we can use the iterative method. In this method, we need to assume an initial value of velocity for each node, and then we can find the U at each cell with the value of neighbor cells. For the next step, we can continue this loop until the x velocity at each node converge to a value. At the end, we'll have the solution of x velocity at all nodes. For our simulation, the density of water is 1,000 kilogram per cubic meter, and the viscosity is 0.001 pascal per second, and the length of each cell is 2 centimeters. We wrote a MATLAB code to solve this equation iteratively. In this code, A represents the number of grids in the x-axis, and B represents the number of grids in the y-axis. The variable q is defined as 4 times mu divided by ρ delta y. In the first loop, we define the x value for each grid. In the second loop, we define the y value for each grid. And in the third loop, we set the initial assumption for the x velocity at each grid. These are the initial conditions. In the main loop, the value of u at each iteration is calculated based on the previous value of u at the nodes for both intermediate and boundary nodes, using the formulation we derived earlier. With 50 cells along the length of the channel and 5 cells along the y-axis, running the code shows that the simulation diverges. This is the contour of initial assumption. However, if we increase the number of nodes, for instance, using 1,000 nodes along the x-axis and 100 nodes along the y-axis, and rerun the code, we obtain results. In the center of the channel, the velocity increases slightly, while near the wall regions, the velocity decreases due to the no-slip condition at the walls. Additionally, we can increase the viscosity. If the viscosity is increased, we observe that the diffusion of the boundary layer into the domain occurs more rapidly. In this session, we solve 3 examples using the finite volume method to become familiar with the FVM. Starting from the next session, we will discuss the governing equations and discretization methods that used by Fluent software.